So this is a presentation for the final project of the machine learning course. The title of this presentation is Machine Learning Reduced Order Model in Programmable Kirigami Structures, and it was done by me, Nicolas Alderete, and Sourabh Saha from the Theoretical and Applied Mechanics program. So we focused on Kirigami metamaterials, which are materials inspired in the Japanese art form of Kirigami, and that comes from the Japanese words kiru, which means cutting, and gami, which means paper. So basically we are doing cuts in materials, and from that we're gaining interesting material properties. The approach of Kirigami metamaterials can be divided into Kirigami lattices and Kirigami elastic engineering. In Kirigami, in the latter one, cuts in the paper or in the sheet of material are used as functionalizing cracks that cause the system to buckle prior to fracture failure. And linear response that arises from the buckling behavior generates out-of-place displacements, which enable a variety of sophisticated three-dimensional shapes. And Kirigami metamaterials are a promising avenue for stretchable electronics, MEMS, and NEMS, which are micro-nano electrical systems, and photonics and phononics. Here in this slide, we can see some of these examples of Kirigami lattices, Kirigami nonlinear springs, and then some more advanced applications of these concepts in sensing, actuation, and energy harvesting. So the problem that we decided to attack was to use a particular Kirigami geometry like the one shown in the slide, which is comprised of a rectangular unit cell with C and U-shaped cuts in it. This Kirigami geometry has been previously numerically and experimentally investigated by us, but only in symmetric cases, and we believe that the fact that we have shown this to work provides a feasibility framework, as can be seen in the video in the corner. And the idea was to use finite elements and with machine learning to predict three key deformation metrics in the system, which are displacements of the red highlighted node segments in the figure. So the first stage was to do some finite element simulations. We generated the geometry by means of doing Sobol sequences to generate pseudo-random sets of geometrical features of the geometry. Then we automated the process of creating these finite element models for more than 150 models. We then conducted a first linear buckling step, which provides the shapes of deformation of the structure. And then we input that as an imperfection in a nonlinear geometric step in which we stretch this Kirigami geometry up to a certain point, and then we obtain the displacement metrics, which are interesting and which we will use to characterize the behavior of the structure.
Hi, this is Sourabh and Ayujan. So the target was to avoid the expensive finite element simulation by using a reduced order model or surrogate model through neural network framework. We have chosen the artificial neural network to be our machine learning technique because the relationship between the input geometrical parameters and output shape of the Kirigami structures is assumed to be a highly nonlinear one. Now, we used two different tools to compare the algorithms of those different tools for neural network building. These tools are the neural network building tool by MATLAB and also the PyTorch. So in both cases, in order to compare, we kept the features of the artificial neural network the same, as in there are 6 hidden layers, and each hidden layer has 10 neurons with hyperbolic tangent as the activation function. Now we designed 3 separate neural networks to attack the problem. One neural network will predict the central line deformation and also the final coordinates of the central line. One will predict the final coordinates of the midspan, the left edge, and other will predict the final deformation and coordinates of the right edge. So there are 3 neural networks with 13 inputs and 3 outputs. Those 3 outputs are the coordinates, and the input contains the geometric information and also the input coordinates. And the training, testing, and validation are data split as 75%, 15%, and 10%. So this is the result of our training from MATLAB. You can see that we got a very good correlation in the nonlinear relationship using artificial neural network. So using the trained network, we try to predict the midspan shape for a random input which was outside the training range, and you can see the result. So the result at this moment of not that promising because of several reasons. First reason is we have to add some more physical constraint as an optimizer to the neural network. Also, we have to couple the edges of right and left to the middle, and also we need to use a larger training set. We have used a training set of 60 simulation, which took us about 2 weeks to prepare. So if we can get more time, then we can build a larger simulation training set, and we can use this machine learning framework to predict the final structure of Kirigami shaped structures, and thus avoid the need for expensive finite element simulation. So this is our whole vision for this work. So we'll try to add to our simulation set as our training set, and we'll try to prepare a neural network using more physically constrained conditions so that we can avoid doing expensive finite element simulation for the design of such Kirigami structures. And these applications are huge. It can be applied for design of sensors, actuators, and photonic devices.
So this is the presentation for the final project of the machine learning course. The title of this presentation is Machine Learning Reduced Order Model in Programming Structures, and it was done by